Consider the line with slope -2/3 and passing through the point 2, 1. Okay. I'm going to draw a graph of this line, and then we'll talk about it for just a minute. So, I'm going to draw some coordinate axes here. I hope you can see this paper all right. So here are my coordinate axes. We have the point 2, 1 is right here. And now using the slope -2, 3, you can find another point on the line. So you can go down 2 and right 3, or you can go up 2 and left 3. So we have the original point, the point 2, 1 is on there. We have this point would be 1, 2, 3, 4, 5, and down 1 is -1, so 5, -1, and we have this point which would be -1 and 3. So, we can find any number of points on this line just by moving back and forth using the slope and thinking of the slope as rise over run. And if we want an equation for this line, we can find one. We could do, say, the point slope form. So we could do y minus 1 using this point equals the slope is -2/3 x minus 2. So there's an equation for that line. And if you write this in slope-intercept form, so just solve this for y. So I'm going to first distribute that slope at -2/3 x plus 4/3, and then add that 1 to both sides. You get -2/3 x plus 7/3. So here's one way to write the equation of a line, actually 3 ways to write the equation of a line. This is the point slope form, this is the slope intercept form, and this is some intermediate form. So there are a lot of different ways to write the equation for this line. Now in terms of writing equations for lines in a sort of linear algebra vector kind of a way, the slope tells you, if you have 1 point on a line, which we were given 1 point on the line, we know the slope of the line. We can start from that 1 point as our sort of launching pad and use the slope to move to any other point we want by just moving some multiple of this slope. So this is going the slope sort of one way, this is going the slope another way. We could find intermediate points by taking fractional values of the slope. And so the slope tells you how to move off of one line and off of 1 point and onto another point on a line. Now, if you consider, say, that a vector, let me put this vector going this way. So now we have a vector, and this vector is what you can call the direction vector of a line. It can play the same role as the slope. So if I know that this point is on the line, and I know that this is a direction vector, and this vector is what's this vector? This vector is the change in x here would be 3, and the change in y would be -2. So clearly there's an intimate relationship between this direction vector, 3, -2, and this slope, -2/3. So I could use, instead of the slope, I could use this vector to move around on this line. I could just take, if I wanted to get, say, to this point, from this point, I could pick my vector 3, 2 up and put it, instead of having, the position vector, I could put the toes of the vector on here, and I would get down to this point. Or I could take half the direction vector, and I would get to that point. Or if I wanted to go from this point to this point, I could take the negative of that vector and move the other direction. So I could start from this point and just take all the constant multiples of that direction vector, and it would give me other points on the line. And so we're going to use the direction vector of the line to write an equation for the line in vector form. So, vector form of a line, you would take a vector, a general vector. So just like here we had a sort of a general point x and y. In the vector form we're going to take a general vector x, y. And we're going to start at any point on this that we know is on the line. Since we were given this point, I'm going to do the 2, 1. Now that's a vector plus some constant multiple of the direction vector. And the direction vector we found was 3, -2. So this is an equation for this line in vector form. Now I've used one point that I knew on the line, and I've used one direction vector, but of course I could write it in a different vector form equation of this line. Could be xy equals, take some other point on the line, -1, 3, and some other direction vector. So any constant multiple of this direction vector is going to be another direction vector, so I could take the negative of it, or -2 times it, so -6 and 4 would also be a direction vector for this line. So they're just like in the regular coordinate geometry kind of stuff that you've been used to doing since junior high school. There are lots and lots, in fact infinitely many ways to write an equation for this line. Same within vector form. So let's just never mind this one. I'm going to scribble that one out. And let's just look at this one and see what this gets us. So what happens here is, here, like when you have a line written in slope-intercept form, this is a nice way to write a line, because if you give me an x, I can give you the corresponding y, and that xy pair is a point on that original line. Here it's a similar deal. If you give me a t, I can give you the vector xy. So when t is equal to 0, I get the vector xy is equal to, when t equals 0, this whole term is going to go away. I'm going to get the vector 2, 1, which is not this point, but it's this vector. And when t is equal to 1, I'm going to get xy is equal to 2, 1 plus 1 times 3, -2 is, what is it, 5, -1. Which again, isn't this point, but it's this. If you draw this as a position vector, it's a vector that, whose position, as a position vector, it's a vector that points at this point on the line. And if we did t equals -1, which I'm going to squeeze in up here, you're going to get xy is equal to 2, 1 minus 1 times 3, -2, which would be -1, 3. Which again is not a point, it's a vector. It's a vector whose position vector points right here. So what's happening here is, if you think about this vector xy being a position vector, and this line of course goes on for forever and ever, so that line goes on for forever and ever. If you had a sort like t equals -2, your position vector would be like over here. So this would be t equals -2, t equals -1, t equals 0, t equals 1. So what's happening is, if you think of the position vector xy as having its very tip here, have a little, like, a light bulb on it, and you take a time lapse, not a time lapse, but a long exposure photograph as t goes from -2 to -1 to 0 to 1, the sort of streak that would leave, the path that the tip of this position vector would sweep out, would be that whole entire line. So that's what's happening there. So you have a parameter here, t, and as t goes from -infinity to infinity, you would be, and it would be all the real numbers. I've just done the integers here, but it would be all the real numbers. You would draw out that entire line. So this is the vector form of the line. We can also write the equation for the line in parametric form. And so what you do here is you'd manipulate this vector equation, and actually perform this operation and the multiplication times t here. So you'd get x, y equals 2 plus 3t and 1 minus 2t. So x would be equal to 2 plus 3t, and y would be equal to 1 minus 2t. And there's that line in parametric form. So vector form here is a vector equation. Parametric form is your x value, your y value in terms of some parameter. In this case, I'm using t. And same thing here. If I plugged in t equals 0, what I would get is I would get the point, let me not do it that way. I would get x equals 2, y equals 1, which would be this point 2, 1, which is the one I used as my starting point in this vector form of the line. So the parameter t equals 0 gives me that point, and t equals 1 is going to give me x equals 5, y equals -1, and so on. T equals -1 would give me x equals -1, y equals 3. And so those correspond to those 3 points that we found on the line also. So this is a way to use the vectors to represent lines and also a parametric representation of lines. So let's do some other examples. Get some fresh paper here. Okay. So let's write equation for the line through, say, 1, 3, and 2, 1. So here we're still in 2 dimensions. We're still in, 8th grade coordinate geometry. So you have the point 1, 1, 2, 3 is right there, and 2, 1 is right here. And you could find the slope of this line by doing rise over run. And you could do the point slope form or the slope intercept form or whatever you wanted to do. But we want to do this in vector form. So we need a direction vector. For the line, and like I say, there are infinitely many of them. They're all going to be on the line. So I'm going to do this direction vector here, from here to here. So that vector, your x would be going up 1, and your y would be going down 2. So there's your direction vector. I'm going to call it D. 1, -2. And you take a starting point, either of these starting points. I'm going to call this the starting point. I'm going to call the starting point, or the vector that we create from the starting point, the vector P. That's 1, 3. And so you get x, y is equal to the starting point, which I've arbitrarily selected as this point. I could just as easily have done that one, plus the parameter times the direction vector, which again is sort of arbitrary. Not entirely arbitrary because it's got to be a vector on this line, but it could be this vector or twice that vector or the negative of that vector, -2 times that vector, whatever vector you prefer as your direction vector. I like the simplest one, so this one or the one going the other way would be the most simple ones to use, just because the numbers are smaller. So here is the line in vector form. In general, the vector form looks like this. Is x, that's your vector, xy, is equal to the vector you create from one or another point that you somehow know is on the line, and that will depend on how the information is given to you, plus a parameter times the direction vector. So there's your vector form right there. It's lovely. And then we could do the same line in parametric form. We would have x is equal to 1 plus t times 1 is t, and y is equal to 3 plus a -2, so that would be, I should do minus, let me grab my eraser, minus 2t. And there it is, in vector form and in parametric form. And you can check this. So, you know, we've used our starting point as this point 1, 3, and so we use the vector that we started with as that point, and see how, if we could get to this point. So what would t have to be in order to land on 2, 1? T would have to be equal to 1, because if t was 1 here, you get 1 plus 1 for the x entry of that vector, and the y would be 3 minus 2 is 1. And same thing here. If you plug in t equals 1, here you're going to get x equals 1 plus 1 is 2, and t equals 1 here is 3 minus 2 is 1. So both of these points do our solution somewhere to these, either this vector equation or this equation. Then we can get this point by plugging in t equals 0. So there are vector form of the line, parametric form of a line, if you're in 2 dimensions. And if you're in 2 dimensions, you're likely to be fairly comfortable, and you can draw a nice picture, and even I can draw a nice picture. If you get into 3 dimensions, the concept is exactly the same, the forms are exactly the same, but drawing a picture of a 3-dimensional situation in 2 dimensions is more difficult. So you can kind of picture it in your head, or try to draw in 3 dimensions. Let's do the line through the points -1, 5, 0, and say 2, 1, 1. Okay, so I want to do it in vector form. So I'm going to need a direction vector, which I'm going to call D. So your direction vector, just like we just did in 2 dimensions, your direction vector is going to be a vector that goes either from this point to this point, or from this point to this point, or a constant multiple of that. So, and those would be constant multiples of each other. So if you do, say from this to this, you do 2 minus a -1 is 3, 1 minus 5 is -4, 1 minus 0 is 1. So there's your direction vector. And the vector that you're going to start at, the starting point, you pick either of these two guys. I'm going to pick the first one again just arbitrarily because it was written first. And so the vector form of the line is going to be x, y, and z is equal to that starting point, -1, 5, 0, plus some constant multiple of 3, -4, 1, the direction vector. And so here is the vector form of this line. And if you look at this again, you plug in t equals 0, you're going to get this point back, or this turned into a vector, the position vector. And if you plug in t equals 1 in here, you get -1 plus 3 as your first coordinate, so it would be 2. 5 plus a -4 is 1, and 0 plus 1 is 1. So there's the vector form for the line that passes through these 2 points. And then the parametric form you get as just a manipulation of this guy. You have x is equal to -1 plus 3t, y is equal to 5 minus 4t, and z is equal to 0, so I'm not going to write it, plus t is just t. So z is equal to t, and there's your parametric form. So depending on what you're doing with these things, this form of the line might be useful, this form of the line might be useful. What we're doing in here in this class in linear algebra right now is just coming up with these equations and trying to get a feel for them. Okay, very good.